Okay, so welcome everyone. Welcome you guys in Darmstadt. Welcome and everyone online. This is the 9th lecture of this year's internet seminar. It's again me, because Sylvie invited Robert to join her in Marseille for first part of this week. So, there was some sort of collaboration, hopefully not against me, but anyway, the effect of all that was that I would give this lecture. But I think for me it's a particularly nice one, so at the same time I'm happy that can be me talking to you about Hardy Littlewood maximal operator. Okay, so that's a huge step away from the things that you've seen over the last 4 weeks. So we already announced in the letter to lecture 8 that this is going to be the finale of our series of lectures about functional calculus. But now, why do we make such a giant leap forwards to something at first sight seems to be completely unrelated? So the idea is to pick up a little bit on the cliffhanger that I left for you at the end of lecture 8, because we were about to investigate fractional powers of divergence form operators, and we had a positive result for fractional powers of exponent less than a half. We had a while ago a positive result for square roots, but we knew that the abstract machinery from this counterexample I mentioned to you would not be sufficient to answer the question about square roots of divergence form operators with non-symmetric coefficients in this generality using just methods from operator theory and functional calculus. And so eventually our ambition is to give exactly that proof to you, because it's going to be a beautiful showcase of how all the different techniques that you can throw at problems related to divergence form operators somehow can be united together and produce a wonderful and deep result. Okay, so that's our idea. Show you how all the different techniques can interact and finally bring different pieces of the puzzle together to eventually solve it. And what we're going to need, the only thing that's missing in our puzzle, is a little bit more about what people call real harmonic analysis related to divergence form operators. And you're going to see today that there's one particular thing, namely averages and maximal functions, that I'm going to introduce today. We're not going to see any divergence form operators in this lecture, but what you're going to see in lecture 9 should be thought of as an additional toolbox that within the next lectures we're going to successively somehow incorporate in the machinery of methods to study divergence form operators. Okay, so chapter 9, or lecture 9, is entitled The Hardy Littlewood Maximal Operator, and there is a general idea behind many of the things that I'm going to do today and on Wednesday, namely that if you have U on Rn locally integrable function that you want to study, or you want to know things about U, and you're gonna find out about U by averaging. Okay, I'm gonna tell you in a second what I mean by average, but just let your intuition do the thing for you and just imagine what you intuitively would think an average is. And then the idea is that properties of this locally integrable function U, they can be deduced by studying averages of U. Then you might think, depending on what your imagination tells you, that just averaging U on size of some fixed size is probably destroy a lot of information. I mean, just think of something quickly oscillating, and then if you average about sets that are too large, you're not gonna detect all these oscillations. But maybe if I study averages of U on multiple scales, in particular letting the scale size shrink to 0, there should be hope that I'm gonna retrieve information about U. Okay, so that's somehow this general idea very basic but important principle in harmonic analysis to know about functions through the study of averages. And so we're going to need a little bit of notation just to ease the work with averages. So I'm going to write for averages the following. So U is the function that I want to average, and E is a set finite non-zero Lebesgue measure, and I write U in a round bracket index E for the average of U and E. That is to say, the integral of U, but normalized with respect to the measure, which I'm going to indicate by this dashed integral. And so this means I'm taking 1 over the measure of E, and then I integrate U over E, so that I'm really computing average value of U on that set E. Right, and then from time to time in this lecture and also in the 10th lecture, we're going to need omega n just as an abbreviation of the measure of the unit ball in Rn. Okay? Measure of unit ball in Rn. All right. Well, that's just notation. Keep it in mind and remember it whenever we're going to use it. And so to start with, what do I want to talk about first to you is just averages and the maximal operator. So this is section 9.1, averages and the maximal operator. Okay. And so to give you an idea of what averages do to a function, let me just take U again, a locally integrable function. And let me take a positive number t, and t you should think of the scale. Okay? So that's the scale. And so this function U as a locally integral function might not have any sort of memorable smoothness properties. But if you look at the averaged version, so as a new function of x, you're going to take U and you're going to average it at scale t around the point x. Then you could use dominated convergence theorem, writing that thing as indicator function and using that the measure of the ball is just independent of x, to prove that this function is continuous. Okay? So that's a continuous function. So to give you a catchy phrase at hand to describe that phenomenon, we might say that averaging smoothens. Okay, that's an experience that you have no matter what sort of idea of averages you have in your mind. You would all agree that if I average, then things get smoother and not rougher. Okay, so this way I can smoothen the function by averages, and then maybe because of the additional smoothness that I introduced through the averaging process, might be easier to study these averages. But the question is, by studying all these averages at all scales t, is there any chance that I get back my function U? Right? So is it true, and that's sort of the open question at this point, is it true that when t goes to 0, then these averages, they give me back U of x? Okay? And this we don't know. It's far from being clear. I mean, we would expect this sort of convergence to happen maybe for almost every x in Rn. Surely we're not going to expect more, because if I take an integral and I alter the function U on a set of 0 measure, this is not going to do anything to the averages. Right, so more than almost everywhere convergence here I cannot expect. But, you know, it's far from being clear. It's far from being clear even if for fixed x these averages remain bounded when t goes to 0. Unless the function is, say, continuous itself. If it's a continuous function, then you can easily check that the averages of a continuous functions converge to the function itself. Okay, so in this game, things work out. Now, I have a reason to call these averages rough averages. So why do I call these averages over balls rough averages? It's because of the following calculation. Okay, this calculation, trivial or stupid as it may look like, it's one thing I want to show you at least once, because I think everyone has to know it when you work with averages and you want to make the link between rough averages and smooth averages to be introduced in a second. And so the observation is just that I can write this integral as a convolution integral. Because if I take, 1 over the measure of this ball, we know precisely what it is. This is like 1 over omega n t to the n, and then this is the integral. Now I'm going to integrate over all of Rn, and I integrate u of y dy, and then I'm going to put just an indicator function here that does the job of giving me exactly the integral over the ball bxt. And the way I do it is I'm going to use the indicator function of the unit ball. So this is the function that says hooray whenever the argument is less than 1 in absolute value. And I should say that in all of the lecture, balls are always open balls. So this function says hooray whenever the argument is less than 1 in norm. So here I want to say hooray if x minus y over t is less than 1 in norm. So this is x minus y over t. Okay? And so now you just put these things together. You see the typical normalizing factor for mollifiers. You see the measure of the unit ball. I put these things inside, and then I can write it as a convolution using some function xi, and xi is going to be the normalized characteristic function of the unit ball. So it's a positive function, the integral of which is 1. And in this language, this omega n goes nicely together with this guy, and then doing this x minus y over t transformation and normalizing by t to the n is exactly what we would do to define the associated mollifier. And so this is nothing else but the convolution of this guy u at possession x. Okay, so this is a way of writing an average as a convolution, and then you see I call it from time to time a rough average because this function here has a jump. It's a non-continuous function. Now then you can probably guess what I would call a smooth average. What would you call a smooth average now? Ideas? What should I do? Please. I convolute with a smooth function. Of course, I just need another guy that is sort of normalized to integral 1. And then this formula with the convolution of this characteristic function tells me that smooth averages, I would probably pick theta smooth and compactly supported functions, say in the unit ball, integral 1, and then the smooth average would be theta of t convoluted with u at x. Okay, and also for the smooth averages, The theorem, you know, is some sort of LP convergence of these smooth averages, viewed as functions of x, but we don't know anything about pointwise convergence of smooth averages towards a function that we're gonna try to reproduce or to study through the use of averages. Now, if you want to prove a thing like that, then maybe you shouldn't shoot for the stars in your first attempt. You should try to prove something simpler. For example, to check that at least these averages remain bounded when t goes to 0. And then you try to control these estimates, say, pointwise for all scales. Here you could write out the convolution integral. You would get something looking exactly like this. If you would just remove the theta by L infinity norm, you would get a similar sort of bound. And then people tend to say that there's a Lord of the Ring principles for these averages, namely there's one operator to rule them all, and this operator is the Hardy Littlewood maximal function, giving the name to this chapter. And this is the operator I'm going to introduce next. Okay, so one to rule them all. No matter if we want to study rough or smooth averages, we want to use the following thing. Central definition of the lecture. So say U is in L1 log on Rn. And now it doesn't matter if it's equivalent classes or functions because I'm averaging, so that takes the ambiguity of the null sets away. And then I'm going to introduce something that I call the maximal function of U, and I'm going to denote it by curly M of U. This is a thing that is defined at each point x in Rn, and it is defined as taking the soup over all averages on balls that could potentially be used to define something that resembles an average of the function around U. So I'm taking the soup over averages, and I'm taking absolute values inside because I want to use that operator to control averages. Okay, so I'm going to take that, and the soup I'm going to take over all balls. So B is always going to be an open ball, and I take all balls that contain X. Not necessarily balls centered at X. I just take everything. Every ball that contains X is going to contribute to this supremum. You're going to see in a second why the definition that you might have expected during my talking, namely to use only balls centered around X, is not the one that we're going to use. Okay, and then the operator M that sends U to this maximal function is called the Hardy Littlewood maximal operator. Okay, so that's an operator sending L1 log things to functions. And so in the first part of this lecture, we're going to see what this operator, this maximal operator, actually does to functions. Just a quick note, this follows just by basically the triangle inequality. If I apply this operator to a sum of two functions, I can put absolute values or not, because this thing anyway produces non-negative quantities, then this is bounded by M of U plus M of V. And also if I throw in scalars into this maximal operator, then it's just going to give me absolute value of lambda times maximal operator of U. Okay, and this lambda thing here, this is just a scalar. And one says in this setting, if an operator M has these properties, you call this a sublinear operator. That is, M is sublinear. Okay, what is not so clear at this point, to be honest, is if this m actually produces a measurable function. Right? You have to think about it for a second, or maybe more, because this is a supremum over a big set. B is not like just supremum of accountable families of measurable functions. So you have to think about it a bit, what this M actually does, even in terms of measurability, before we can do more advanced stuff. But fortunately, next lemma says that M of u is always going to be a measurable function. It's even better. Namely, M of u as a function from Rn to extended positive numbers is lower semi-continuous. LSC for the cool kids. So what does that mean? You guys remember what lower semi-continuity is? I'll be fair, I'm gonna recall it in the proof. We also recall it in the lecture notes. Okay, so lower semi-continuity means the following thing. That for every lambda larger or equal to 0, we have that the super level set of M of u, so the function under consideration, the super level set of level lambda is going to be an open set. So O lambda going to be defined as the set of all x in Rn, such that M of u at x is strictly larger than lambda. This is open. This is the definition of lower semi-continuity and instability, because it means that the pre-images of these open intervals from lambda to infinity for every lambda be open. So, but it's a little bit better. Now, you're going to see in this proof why working with this uncentered maximal function, because B is not centered in X, sometimes allows for particular easy arguments. In particular, this is going to be more or less a no-brainer. Because suppose that X would be in O lambda. I need to prove that O lambda is open, so I have to fill a neighborhood of X into O lambda. Now, what does X in O lambda mean? It means the maximal operator got strictly larger than lambda. So this means that the sup got strictly larger than lambda. So there has to be a ball that already by itself produces an average that is strictly larger than lambda. So it means there exists a ball. B is always going to be a ball, unless I say something else, which I'm never going to do. There exists a ball B that contains X with the property that the average of absolute value of u on this ball is strictly larger than lambda. That's just the definition. Agreed? But if I take any other point in this ball B, the fact that this average was larger than lambda on this ball B means that every other point in B also belongs to the set O lambda. Because this thing means that for every point in B, the uncentered operator is going to be larger than lambda. So I can just conclude from that B is going to be a subset of O lambda, and B contains X. So that's already the proof. Very easy. If I would have used a centered version, proofs are slightly complicated, more complicated from time to time. There are also arguments that become easier, so it's a choice that you can make. But what you should keep in mind is that if x is sitting somewhere in Rn, okay, let's draw it here. So x is sitting here, and I have any ball B that contains x, then I can take a ball of double the radius of B, and this ball will be centered at x, and it will contain B. Okay, so this radius is twice the radius of B. Okay, so uncentered balls are more general than centered balls at x, but every uncentered ball is contained in a centered ball at x of twice the radius. Okay, and then because in this process measures are comparable, if I would have taken uncentered version of the maximal function or centered version, it just gives comparable operators up to a constant. Okay? So we stick with this one. Now, my question is, how does M behave on LP of Rn when P is between 1 and infinity? And I'd say there's one case that is extremely easy. Namely, when P is equal to infinity. Imagine U would be an essentially bounded function. Okay. This case is easy. Why? I take any average on a ball B that contains X. On this ball B, because U is essentially bounded, I know that absolute value of U is less than the constant U L infinity norm almost everywhere. So this average is less than averaging a constant. Well, if you average a constant, then you just get back the constant. So every single average is less or equal to U in infinity norm. Now, because this works for every x, this means the maximal operator is bounded by U in L infinity for every x. This means the maximal function itself is also L infinity. And I conclude, because this is mu at x, I conclude that the maximal operator in L infinity, maximal operator is bounded on L infinity with a bound 1. Okay. That's the easiest of all cases. Now, on the other side of the LP scale, I mean, that would be the next case, right? L infinity is done. Great, effortlessly we did it. What's going to happen for P is equal to 1? And here, and that might be to your surprise, this case is impossible. Impossible in the following sense. What number should that lemma get? By the way, I should call this equation over there 9.1. I'm going to do that later on, and that should be 9.4. A lemma. Lemma says the following. If simultaneously U is locally integrable and its maximal function is L1, these two things together imply that U is 0 almost everywhere. Okay, so in particular, except for the trivial zero functions, there is no function in L1 for which the maximal operator maps into L1. Now, because I'm going to need that a bunch of times, let me call this fact 9.1. So that's surprising, right? Probably not what you've been expecting. And the proof is also not complicated. How does it go? So suppose I want to prove that U is 0 almost everywhere. I'm going to fix any positive number R, and I'm going to show that absolute value of U is 0 almost everywhere on the ball of radius R around the origin. This is going to take care of that. And in order to show that U is going to be 0 almost everywhere in that ball, I just have to prove that the integral of absolute value of U is 0. And this is what I'm going to do as follows. So I'm going to work with X, the absolute value of which is larger than R. And I'm going to do following estimation. So I start with a maximal function of U at X, which is an integrable function by assumption. Now I'm going to bound that from below multiple times. The first thing is this is the soup over all averages on balls that contain X. So a particular ball that is admissible would be to take a ball of radius twice norm of X around the origin. Alright, and I sort of write out what that is. This is 1 over omega n, the measure, then it's going to be 2 absolute value of X to the power of n. And then I would be this is just taking care of the dash here, right? So the dash produces this, and then I would have been left with the integral over that ball. And because X is larger than R in absolute value, this is actually larger than integrating over this fixed ball. Okay, and then you should think of that guy here. This is a constant because R is fixed. Now you see, this function here is integrable by assumption. On the set of admissible X, so the set of all X, the norm of which is larger or equal to 0. By this guy, this is 1 over absolute value of X to the n. This is the critical power that's neither integrable at the origin nor at infinity. So this guy here is not integrable on the same set. So how could it ever be true that an integrable function controls up to constant a non-integrable function? Well, there's only one way out, and the one way out is that the constant has to be 0. So C is going to be 0, and so U vanishes almost everywhere on the ball, and we have the proof. Okay, from this argument, you might get the impression that the integrability of the maximal function fails because of the global properties on Rn, because this was an argument that uses m of u at x, where x is going to be far away from the origin. But in the exercises, you're going to learn that m of u integrability can even fail locally. Okay? So in the exercises, m of u in L1 lock can also fail. In other words, on L1, with the traditional idea of norm bounds, there's very little hope. But, and that's our first main result for today, there is a weaker type of L1 bound that is going to be true when U is in L1. And that's the following thing. So suppose, still following this question, behavior on LP for p is equal to 1. So suppose u is in L1 on Rn. We know that the maximal function in all non-trivial cases is never going to be in L1, but there's something close to L1 but a little bit weaker, which looks as follows. For all lambda positive, we have the following thing. If I look at the measure of the set of points on which m of u is larger than lambda, so I'm looking at the super level set O lambda from the proof above, then I have a reasonable control on this measure by 3 over n, 3 to the n over lambda times u in L1 norm. And I'm going to call this thing here a weak type bound. And the reason why I call it a weak type bound is basically Markov's inequality. So if v is any function in L1, say, and lambda is a positive number, then what is always true is that the measure of the super level separable function at height lambda, this is going to be controlled if I multiply it by lambda by v in L1 norm. And this is called Markov's inequality that you know from measure and integration. Okay, so Markov's inequality says this is always true. And so the thing is, if in the claim of theorem 9.5 you would move this lambda to the other side, you would see that the maximal function also is one of the functions v that has the property that measure of the super level set times height of the super level set is uniformly bounded with respect to lambda. It's just that the maximal function is not L1 itself. Right? So the boundedness that goes here and saying that if I multiply by lambda, then this is uniformly bounded in lambda. For L1 functions, it's automatic by Markov's inequality. But what we've seen before is that maximal functions of L1 functions are examples of functions that do have this property, even though they are not L1 itself. Do you have questions on that? If not, then I'm going to do the proof of that. I'm going to need 2 lemmas to do that. We'll make a break, and then we fiddle it together and go on. Okay, so we need 2 lemmas. Should I give a number to this thing in order to... Yeah, Markov's inequality should be 9.2. Okay, so 9.6 is the world famous layer cake formula. And it goes as follows. So P, say, is a number between 0 and infinity. And U is a measurable function on a sigma finite measure space x mu going into the complex numbers, and then the layer cake formula gives you a layer cake formula for the p norm. So the integral of u of x to the power p with respect to the measure This norm you can construct from looking at the layers of the cake, so the superlevel sets. So if you take consistently the measure of all x in x such that u of x is larger than lambda, and you're going to integrate that in lambda, then it's just missing a factor of p lambda to the p minus 1, and that's the formula. Gives you a means of weighing the measure of the superlevel sets in order to reconstruct. You've probably seen that for p is equal to 1 in courses on measure theory or probability theory. Proof is not hard. It's just one trick that one has to remember. So I start with the left-hand side, and then I'm going to look at u of x absolute value as a number, and artificially I'm going to write that number as an integral. And the way I can do it is I can go from 0 to this number u of x, and then I need to integrate the derivative of the power p function. So lambda, so p times lambda p minus 1 d lambda, and this is going to be a d mu of x. D mu of x. Right? Because it's in the integral, and lambda with this dummy variable just gives me u of x to the power p. Alright, and now the only thing you have to do is Tonelli. Because look what happens when I apply to Tonelli to this integral. So I want to switch the order. Now lambda is running from 0 to this positive number with all possibilities. So after changing integration, lambda should be running from 0 to infinity. So we get that. Then p lambda p minus 1 is already there. The only thing I have to worry about is when I do integration the other way around, lambda being fixed, what do I pick up in x? Well, first of all, there's no function anymore that depends on x, so I'm just integrating the one function, and I just have to make sure to understand on which domain I'm integrating. Well, the domain is precisely the set of all x for which u of x in absolute value is larger than lambda, because it's the condition that comes up from this integral. So I'm picking up on this set, the integral of the one function with respect to mu is precisely the measure. So just apply Tonelli and we get the claim. Okay. Second lemma I need is a covering lemma called Vitali covering lemma. Why do we need a covering lemma? Well, you can imagine if I want to bound the measure of the superlevel set of the maximal function, if I know that the maximal function is large, then just the proof of the lower semi-continuity, I'm going to get a bunch of balls where averages are larger than lambda. But if I want to prove a reasonable estimate for that, I need to make sure that I'm not just picking balls that overlap all the time. You're going to see that very precisely in the proof of the Hardy Littlewood 1 theorem. Maybe the idea already becomes clear in your mind, and Vitali covering lemma is a way of extracting from an arbitrary cover, finite cover of a set by balls, a subcollection of disjoint balls that also cover your given set in a very specific sense. And this very specific sense is as follows. I let script be finite collection of balls. recalling that balls for me always means open balls, then there exists a disjoint subcollection script B prime of B with the following property. All space that is occupied by taking the union of the balls in my given collection B can be covered by just this disjoint subcollection. Agree? No, this is never going to be true. I mean, how should that ever be true? This is just nonsense, but up to factor of 3 it is not nonsense. I just need to blow up the balls by factor of 3. So by this I mean this thing here is concentric to B prime with 3 times the radius. Right, so if B prime, say, is the ball at x of radius r, then 3B prime is going to be the ball of centered around x of radius 3 times r. Okay, so up to blowing up the balls by a factor of 3, you can restrict yourself to disjoint collection of balls. You can convince yourself that 3 is the best constant I can use for this purpose. Just think of the extreme case being 2 balls of the same size that touch, and then if they just overlap ever so slightly, then you're going to need at least 3 minus epsilon blow up for one of the balls to cover the other one. They just touch, then they're disjoint, so there's no purpose, but if they slightly overlap, then you need to blow up this guy by a factor of at least 3 minus epsilon to become big. Okay. So here's the proof. The proof is not complicated. B is a finite collection of balls. So we order B in decreasing manner. And we're going to write B1, B2, and so on and so forth until Bn. Okay? Decreasing manner, let's say like this. Order B with decreasing radius. Right, so what should decreasing mean? I take the B1 as the ball with largest radius, and then I order them in a way that the succession of radii is decreasing. Okay, and now I'm going to select the balls for B prime in a greedy way. I just take the largest piece I'm allowed to take every time I have to take something. So the greedy algorithm goes like this. We're going to select B1. Oh, now my phone's ringing all the time. Should I take the phone call maybe? What do you think? Oh, it says the kindergarten of my kids is going to be closed next week. Okay. Select B1. So I take the largest ball. And then for J from 2 to the n, I do the following thing. I'm going to pick Bj if I'm allowed to pick it, and I'm allowed to pick it if it is disjoint to every previously selected ball. So I'm going to select Bj if it is disjoint to all previously selected balls, and else I'm going to discard it. Right? Just go through it, and every time I still have to pick something, I pick the largest possible thing if it's admissible. So that's That's the algorithm to prove the Vitali covering lemma. So clearly produces a disjoint collection. Because before making any choice, I'm always going to check for disjointness. So we're going to call the collection that is returned by the algorithm, I'm going to call it P prime, and what I need to prove is the 3 covering property. So I take any x in Bj for any j, and I need to prove that this point is contained in the union of the 3 B prime, where B prime just runs over the new collection B prime. Okay. So if j is selected, well, there's nothing to do. If I selected Bj, then it's already over, because if Bj was selected, I don't have to prove anything. It is even in the union of the boards without the enlargement factor. So suppose Bj was discarded by the algorithm. Now, how could that ever happen, that the algorithm throws away our friend Bj? That was, at some point the algorithm checked Bj and it failed. So it was the case that there is an index k that came beforehand, such that Bj intersected Bk was not empty. So it contains some element I'm going to call y. The only way the algorithm could have discarded it. So now I write Bj as B xj rj, just trying to indicate center and radius of my balls. And I want to check that my element x is contained in 3 times Bk, because Bk was selected. Okay, I should add that here. And this ball here has been selected, because it was one of the things that has been previously selected and the check failed. Okay, so I need to check distance of x to xk. I'm used to triangle inequality to fill in every information I possibly have at hand. So what I can do is I can compare x with the center of Bj. I can compare xj with y, and y I can compare with xk, and then you see, because x was in Bj, this is less than rj. Because y also was in Bj, this is less than rj. Because y is also in Bk, this is less than rk. But k came before j, so this is less than rk, and this is less than rk, and so all of this is less than 3 times rk, and I checked that x is in 3 times Bk, and the proof is accomplished. Okay, let's make a break here, and I'm going to clean the board for everyone, and then we're going to continue. So let's resume at, say, 45. All right, so because for the Vitali covering lemma, I only can work with a finite collections of balls, and I also use that. And by the way, the claim, as I stated, is also wrong for infinite collections. I need to use some compactness argument. And so what I want to do is I want to estimate the measure of this set, and I can use the interior regularity of Lebesgue measure to say it's enough to prove actually that every compact subset of O lambda, so K is going to be a compact set, every compact subset of O lambda is bounded in measure by what I want to prove. If that works for every compact subset of all of O lambda, then I'm also going to have the bound with O lambda itself. Good. So now K is fixed, and I claim I can cover K by balls with the following property. This is going to be 9 point. No matter how good I keep the lecture in mind, I never make the numbers right. I'm claiming I can cover K by balls with the property that the average on B of absolute value of U is going to be larger than lambda. And that just works because every point that is contained in O lambda is contained in a ball with this property by the defining property of the super level sets. Okay, and so for every point I get a ball, then I can just take all balls that I can possibly get from that. That gives me a covering of also O lambda, but K in particular, because now K is compact, I can pick a finite subcovering. Right, and this is where compactness is used. So now, compactness and Vitali allow me to do the following thing. I can cover K by a bunch of balls B in some collection B prime, and this B they are B, and they always have property 9.3, but it's a finite collection. Okay. That's the point where I use compactness. So I get a finite number of balls K with a property 9.3 that still cover my compact set K, and from these I can extract a finite subcollection of pairwise disjoint balls, so B prime in B prime, and I cover by 3 B prime, and this is a disjoint collection. And now you're going to see why I need that Vitali covering part in the argument. Okay, so thus, I want to estimate the measure of K. Well, K is contained in a union of balls. So I can bound the measure of K by the sum over B prime in B prime, and I use the balls 3B prime. It's just what follows from the covering property. Now, the measure of 3 times B prime, this is 3 to the n. Now that's a good sign, because now the 3 to the n is showing up in the estimate already, times the measure of B prime. Now B prime is a member in particular of B, so B prime has the property 9.3. So let me quickly get back to 9.3 and just rewrite the estimate in the way I'm going to use it. So I'm going to use it for a ball B prime. I'm going to put the average away by multiplying by the measure of B prime. So B prime is going to appear on the right hand side, and then I'm going to cancel the lambda, and I'm going to put a 1 over lambda here. And then you see measure of B prime is precisely the term that I'm having here. So now I use 9.3 to continue my estimate. So I can bound that by the sum B prime in the disjoint collection, 3 to the n times 3 to the n over lambda times the integral on b prime of absolute value of u dy. And now comes the point where I'm using disjointness, because the constant goes out of the integral, then I'm summing over this collection of balls the integral of the absolute value of u on each ball, but because the balls are disjoint, there's no overlap, and the sum of the integrals is certainly not going to be larger than the integral of absolute value of u itself. Right, so because of disjointness, I can just brutally estimate this by u in L1 norm, because there's no overlap. And then this is already the proof. Mission accomplished. Do you have questions? Yes, please. Yeah, just use. So the question was on the notation. Yeah, I'm not going to use it consistently. It's just in this proof, it just means that K is a compact set and is contained in O lambda. I shouldn't have used the double inclusion notation. And it's not a thing that I'm going to use longer. I just wanted to not write K is compact. Okay? Other questions? All right, so we have a result at L infinity. That was very easy. Now we have a result in L1. So now the next question is it okay to say that M is controlled on L1 and L infinity, hence controlled on LP, when P is between 1 and infinity? Okay? That's a valid question. It's a question of interpolation. We're going to write down an exercise for you in case you've never seen interpolation before that elaborates a little bit more on this idea and makes more precise in which sense there's a general principle that's going to appear in the proof. But the proof I'm going to do now is the first and probably easiest showcase of the general principle. And we will see that indeed the control on L infinity plus the weak type control in L1, this gives control in LP norm for all P in between. So this is 9.8, Theorem, Hardy Littlewood 2. And it says that if P is between 1 and infinity and U is in LP Rn, then the maximal function of U is also going to be LP, and I have a bound of the maximal operator LP to LP. This is less than a constant times U in P, and you can say what the constant is if you like that. A constant that works is twice P R to the n over P minus 1 to the 1 over P. The precise value of the constant is not important, it's also not optimal, but it's the constant that's going to be produced by our argument. All right, so it's the best possible thing, and the interesting thing here is that for P is equal to 1, the statement is false, but by this interpolation thing, for all P larger than 1, it's going to be true. So, how do we do the proof? Of course, we fix U, and we let P between 1 and infinity, and I start by writing out just the quantity that I want to estimate. So what I want to estimate is the norm of the maximal function in LP, and for convenience I'm going to put it to the power of P so that I don't have to carry big brackets and 1 over P's in the argument. And I'm going to need something that is playing well with the things that I already know about the maximal function. And if you look at that, I know something about super level sets of the maximal function. So I'm going to use the layer cake formula to write the norm of the maximal function with respect to super level sets. So this is going to be layer cake formula was what? 9 point. Okay, it's a layer cake formula. Just say layer cake. Okay, so it's p times lambda p minus 1, and then we have the measure of the super level set of the maximal function. All right, so we're not going to get away with that, because good control on these super level sets comes under the assumption that U is L1, but now U is LP, and P is bigger than 1. All right, so what's the issue going from LP, from L1 to LP? Well, being integrable to the power P is easier when you take small values, because then the pth power is smaller than the one, just the function itself. For large values of the function, being integrable to power p is more restrictive than being integrable. Okay, so that tells us that there's a game going on, and if I want to use that estimate above, I have to make sure that u does not take small values. Okay. So what I'm going to do is I'm going to chop off the small values of u. I treat it by one method, and then the large values I treat using what I have above. And there's tons of possibilities to do that. And because we're doing something for all sorts of level sets, I'm gonna link the level at which I chop off u with the level of the super level set itself. So split off large values of u. This is what I want to do here in this sort of intermezzo. I'm going to write u as the indicator function. Now I'm using some shorthand notation. I'm using the indicator function of the set of all x where absolute value of u is larger than lambda over 2, and I'm using the indicator function of the set where u is less than lambda over 2. Okay, that's a decomposition I can do, and I'm going to call this function, I'm going to call v, and this function I'm going to call w, and then w in infinity norm is less than lambda over 2. Okay, so w captures all the small values of u with respect to the scale on which we're working, and v captures all the large values. And so that means that the maximal function m of u is pointwisely controlled. You use sublinearity, you get the maximal function of v plus the maximal function of w, but because w is bounded by lambda over 2, I can just put lambda over 2 here. Okay, so I have this pointwise control of the maximal function, and now from this intermezzo, what I'm getting is that the super level set of the maximal operator applied to u at level lambda, I'm looking at values of x where the maximal function is larger than lambda. Well, if the maximal function of u is larger than lambda, then the maximal function of v has to be larger than lambda over 2, because they just differ by this lambda over 2. Okay, so this is contained in the set of all x such that the maximal function of v is going to be larger than lambda over 2. This guy larger than lambda can only be true if this guy is larger than lambda over 2. Just bring lambda over 2 to the other side. So I have an inclusion, and now I'm going to take measures. So then this is a less or equal, and I can bound the measure. Now, you could check that this v function is actually L1. We don't need it in the argument, but you could do that. In any case, I can just write down by 9.5 that this is less than 3 over n over lambda over 2 times v in one norm. Okay, if one norm would be infinite, that would also be true, but in fact, by what I told you, the part of u where u takes large values, the p integrability is stronger than integrability, though this v is going to be L1. Yeah, so that's all I want to do. Now, where do we go on? Maybe do a nonlinear version of the lecture and continue here. So 9.4. yields the following. So m of u, p norm to the p, is going to be, now I'm inserting the bound on the super level sets, so it gives me 3 to the n, and it gives me an integral from 0 to infinity. Now I have to play a little bit with the powers of lambda, so it's going to be 2p, then it's going to be lambda power p minus 2, because I'm dividing out one further lambda, and then this is going to be v in the one norm, the lambda, and the one norm I'm going to write as the integral over the set where u is larger than lambda over 2, absolute value of u dy d lambda. Okay, so that's what the estimate sort of produces for me. And now you see I want to get back to the LP norm of u, so I need to do Tonelli. Okay, and so what does Tonelli give me? Let me write u of y here to be more precise. So the 3 of n over n clearly stays outside. Then I want to integrate in lambda first, and then I want to integrate in y. Y can be anything on Rn, and the thing that depends on y is going to be the u of y absolute value. And then I'm going to integrate in lambda something like 2 to the p lambda p minus 2 d lambda, and I just need to get the borders for the integral right. So absolute value of u was larger than lambda over 2, meaning that lambda goes from 0 to twice absolute value of u of y. So that was Tonelli. And now that's an integral you can compute. This gives you 2p over p minus 1 times 2 absolute value of u to the power p minus 1. Just take antiderivative of this p minus 2 function. And then if you play it all together, then you see you get some constant crap, and the crap turns out to be exactly the c, so that's what c stands for. And what remains after the lambda integral is gone is absolute value of u to some power, and the power is, well, here it's 1, and here it's p minus 1, so this gives exactly power of p, so it gives u in p norm to the p, and that's the thing that we wanted to prove, and the proof is complete. Do you have questions? No. Okay, so we have the bound for the maximal operator on LP for every p except for 1, and for p is equal to 1 we have the weak type bound. Now in the next parts of this lecture, part of which is going to be today, part of which is going to be on Wednesday, we're going to explore a little bit further, first of all, what these bounds imply. And one beautiful application is the first one, is about Lebesgue differentiation. Okay, that's the thing I want to do with you still today, and then the rest is for Wednesday. And so what is Lebesgue differentiation about? It brings us back to the question I raised at the very beginning. now that I have control about the maximal function, which is the function that rules all sorts of averages, is that enough to prove something about pointwise convergence of averages? Okay, so I'm going to take u from Rn to C locally integrable function. No equivalence class, really a function, so that I can speak about pointwise values. And I take a scale, t positive, and I want to compare, as at the very beginning, I want to compare the average of u at scale y with the value of u at x. And ideally, sending scale to 0 will reproduce the function, meaning that this term goes to 0. Okay, so there's one trick. It's always good to keep in mind when you work with averages, is that you can write it also as u of y minus u of x dy. You can bring the constant inside because the normalization makes integration being with respect to like a probability measure on that set. And so you can write it like this. And you can even be more generous. You can bound it. You bring the absolute value inside. And then you have this estimate. And so having this thing tend to 0 is a stronger requirement than having these averages converge. And actually, we're going to focus on that. And the theorem I want to prove with you in the remainder of the lecture is that this gives us convergence. Okay, now I should say, if u is continuous at x, then I could bound this by the sup for all y distance to x less than t of u of y minus u of x. And so if u would be continuous, then this, as t goes to 0, goes to 0. Right, so for a continuous function that works, that's probably no surprise. Then you know that smooth and compactly supported functions, they are dense in, say, L1. And so there could be hope that you can use the denseness of these good functions to somehow carry over this convergence property to more general functions. And we're going to see that in our first try to do so, we have to deal with a two-parameter family of things, and we have to handle the limit somehow simultaneously in these two things, because we want to pass to the limit in the scale, and we want to get close to our function by a good function, but we cannot do both things at the same time, and the way out will be exactly the weak type bound for the Hardy Littlewood maximal operator. It is exactly what you're going to need in order to make the proof I'm going to show to you work. Okay, so this is what? Theorem 9.9 about Lebesgue differentiation. I'm going to talk at the beginning of next lecture a little bit more about what we call it differentiation. Okay, so u is as before locally integrable, and then it's going to be true for almost every x in Rn. You have that the limit as t goes to 0 of these averages, so u of y minus u of x dy, this really goes to 0. Okay, and if that happens at x, x is called a Lebesgue point. Okay, so the points at which this happens, they're called Lebesgue points. In the lecture notes, this is remark 9.10. Okay, the proof is not complicated, but it uses one argument that hopefully is convincing for you. I claim that without loss of generality, I can assume that U is integrable. And the reason is that this is a local claim I'm trying to prove. I position myself somewhere in space, and then I want to look at averages on small scale. So what happens for U outside of that window is completely irrelevant for what happens at my finger. So if U is not integrable, I just replace U by U multiplied by the indicator function of a huge ball on which I want to work, and then I prove it for all huge balls, and the claim localizes and it's all fine. So we're going to assume that U is integrable. And many of these problems, they have their own specific maximal function. And I'm claiming that for this, solving this specific problem, there is another maximal function that we should look at. And then we're going to see that the Hardy Littlewood maximal function by the Lord of the Ring principle is also going to rule this new maximal function. And the maximal function I should be studying in order to solve that problem is, well, I do not yet know that this thing has a limit. But it's a bunch of positive quantities. I could just look at the lim sup in T and then hope that it's 0 all the time. Then this also proves convergence. So I'm going to use U star of x to denote the lim sup as T goes to 0 of the thing I want to look at. Okay, and then convergence in this sense is equally good as saying that U star at x vanishes. And then I'm going to use the usual measure theory trick. I'm going to look at super level sets, O lambda. They are all x in Rn, for which U star at x is larger than lambda. Now, if I want to prove that U star is equal to 0 almost everywhere, it's enough to prove that all of these sets here are null sets. Then U star has no chance then taking the value 0 all the time. Okay, so goal, all O lambda are null sets. Okay, so I'm going to fix lambda, and I'm going to prove that O lambda is a null set. So I'm going to show that the measure of O lambda is less, lambda is fixed. Okay, so fix lambda. I'm going to show that the measure of O lambda is controlled by epsilon, where epsilon is any threshold that I can put myself as a limitation. Okay, so let epsilon be positive. I was thinking just when I prepared this lecture, and I looked again at the lecture notes, if it would be really the first time that we write let epsilon be positive. I'm not sure, but it could be. Okay, and so I can pick a function v in CC infinity that is epsilon close to u in L1 norm. Right? This was something we discussed in lecture 3. And now I want to bound u lambda of x. Well, u lambda of x is this limit superior thing, and I'm just doing the triangle inequality in the integral to introduce the v. So lim sup as t goes to 0, average on b xt, I do u of y minus v of y, I do v of y minus v of x, and I do v of x minus u of x dy. It's just the only thing I can do, because there's u of y, there's u of x. I want to use closeness of v to u, so I have to introduce all these terms. Now we need color, because I said that this auxiliary maximal function, at least this is how I think about the u star, is adapted to the problem. And adapted to the problem here also means, because we know that what we're trying to prove is true if the function is continuous, it's going to be true for v, okay? And so this part here you can ignore in the limit superior, because this will tend to 0. Okay? This goes to 0 as t goes to 0 by continuity. Now this thing here, this is just averages of u minus v. I can bound it by the maximal operator. So this is less than m of u minus v at x. And that guy over here doesn't even depend on y, let alone the scale t. So this is just u of x minus v of x. Right? So the maximal function was adapted to the problem, and the v star, if you want, so v star is 0. And here you see I have to play a game. I have to say how close u is to v, but then the scale changes at the whole time, but the Hardy Littlewood operator is just there, and it takes care of this problem, potential problem. All right, so to come to an end, I have to look at super level sets of u star. So if u star of x is larger than lambda, this means the left-hand side is larger than lambda, then one of these two guys has to be larger than lambda over 2. One of the terms on right-hand side is larger than lambda over 2. It's a similar argument to what we've seen before. And so this means that I control the measure of O lambda by the measure, sum of the measure of two sets, super level set of the maximal function of u minus v, and just level set, a super level set of the function u minus v. U minus v at x larger than lambda over 2. Now I want to gain control on that thing. I can use Theorem 9.5. Yep, 9.5 takes care of the first thing. So by 9.5, this is less than 3 over n divided by lambda over 2 times u minus v in one norm. And here I can simply use Markov, and I get 1 over lambda over 2 times u minus v in one norm. Okay, so this was the easy term, because this one was the one that was not changing when I do limits in the scale. And by my choice of u, I can say this is less than 1 over lambda over 2 times epsilon. So it's epsilon small. This guy was the complicated guy, because I have to somehow deal simultaneously with v being close to u and the scale t changing all the time, but they're controlled by the maximal operator, and I still have the same type of bound, except for this additional constant 3 over n. So this is also epsilon small. So this means the set O lambda has epsilon small measure, but epsilon is arbitrary. So because epsilon was arbitrary, follows that O lambda is a null set, and then we are done. All right, so that's all for today. I'm going to see you on Wednesday, and of course I'm going to stay here if you have further questions. Is there a question you want to pose while video is still running? If not, then don't be shy and ask me after the lecture, and I see you all on Wednesday.